Somewhere in the universe right now, there's a black hole that should not exist. Not according to the models, not according to the timelines, not according to anything scientists thought they understood about how the cosmos builds itself across billions of years. And the James Webb Space Telescope found it sitting there in the early universe looking fully formed and enormous, and completely unconcerned with the problem it was creating for the people trying to explain it. This is where the story of black holes in 2024 actually begins, not with the familiar facts about stellar collapse and event horizons, with a discovery that is forcing astronomers to reconsider some of the most fundamental assumptions about how the universe assembled itself in the first place. The object is called QS01. It sits approximately 13 billion light years away from us. That distance means the light we are receiving from it left its source when the universe was only about 700 million years old. The universe, as best we can currently measure it, is approximately 13.8 billion years old. So we are looking at something that existed when the cosmos was barely 5% of its current age. At the center of QS01 sits a supermassive black hole with a mass approximately 50 million times greater than our Sun. 50 million solar masses, in a universe that was 700 million years old. The problem is not the number itself. The problem is the timeline. Based on everything scientists understood about how black holes grow, the processes available in the early universe should not have been sufficient to produce something that massive, that quickly. Black holes grow by consuming material, gas, dust, stars. Other black holes, each meal adds mass, but meals take time. And the time available before QS01 was fully formed was not enough by any conventional calculation to explain what Webb found sitting there. But here is what makes this discovery genuinely strange, rather than just mathematically inconvenient. The black hole at the center of QS01 is not the right size relative to the galaxy surrounding it. In every galaxy that astronomers have studied in detail, the relationship between the central black hole and the host galaxy follows a consistent pattern. The black hole is massive, but the galaxy is vastly more massive. The two structures grew together, and the black hole ended up representing a specific, small fraction of the total mass. QS01 breaks that pattern completely. The galaxy around the black hole is surprisingly small and underdeveloped. The black hole represents a disproportionately large percentage of the total mass of the system. If you tried to describe it in physical terms, it is like finding a fully constructed skyscraper standing alone in an empty field before the city around it has been built. The central structure is enormous and complete. The surrounding environment has barely begun to develop. What makes this scientifically significant beyond the strangeness of the individual case is that QS01 is not alone. Since Webb began its observations, astronomers have been cataloging objects in the early universe that share similar characteristics. They have an informal name for them, little red dots, small distant objects that appear to host surprisingly massive black holes given their age and the size of their surrounding galaxies. Webb has already found hundreds of them. The pattern is not an anomaly, it is a population. And a population requires an explanation. The leading theories about how these objects form divide roughly into two camps, and both of them require abandoning some previously comfortable assumptions. The first possibility is that the black holes at the center of these early systems did not form through the normal stellar collapse pathway at all. In the standard model, a massive star exhausts its nuclear fuel and collapses. If the star was large enough, the collapse produces a black hole. That black hole then grows over time by consuming surrounding material. But this pathway has a speed limit. You can only consume material as fast as physics allows, and the early universe did not have billions of years for this process to run. The alternative proposed by some researchers is that under the specific conditions of the very early universe, massive clouds of gas could have collapsed directly into black hole seeds significantly larger than anything produced by stellar collapse. This would give these objects a substantial head start on the growth timeline and potentially explain how they reached 50 million solar masses before the universe reached its first billion years. The second possibility involves dark matter. Dark matter is the term astronomers use for whatever is providing the gravitational scaffolding of the universe that visible matter alone cannot account for. It constitutes approximately 27% of the total mass energy content of the cosmos, and by definition does not interact with light. It cannot be directly observed. Its presence is inferred from its gravitational effects on things that can be observed. Some researchers have proposed that dark matter dynamics in the early universe could have facilitated the formation of unusually massive structures before the processes that dominated later cosmic evolution had fully established themselves. Neither of these explanations has been confirmed. What they share is a willingness to consider that the universe in its earliest phase may have operated under conditions that produced outcomes not fully anticipated by models built from observations of the mature cosmos. There is a third possibility that is the most conceptually radical, and the one that has generated the most discussion. What if the causal relationship between galaxies and supermassive black holes sometimes runs in the opposite direction from what we assumed? The standard picture has galaxies forming first, and black holes emerging within them and growing within the gravitational structure the galaxy provides. But QS01 and the little red dots raise the question of whether at least some supermassive black holes might have formed before their host galaxies, and might have provided the gravitational anchor around which the surrounding galaxy subsequently assembled. Not galaxies building black holes, but black holes building galaxies. This inversion would represent a significant revision to the standard model of galaxy formation. It would not invalidate that model for the majority of the galaxies we observe, but it would mean the relationship between these two types of structures is more bidirectional and more complex than the existing framework acknowledged. Now shift from the very distant to the relatively nearby. 5,000 light-years from Earth within our own Milky Way galaxy, astronomers have detected something that has never been detected before. A black hole traveling alone through space with no companion star, no surrounding galaxy, no context that would normally make it detectable at all. Just a black hole drifting through the stellar neighborhood with nothing to eat and no obvious reason for being where it is. Surrounding gas glow and X-rays, or when they are paired with a companion star whose orbital behavior betrays the presence of something massive and dark. Remove those circumstances, and a black hole becomes essentially invisible against the backdrop of space. The detection of this particular wandering black hole required a technique called gravitational microlensing. When any massive object passes between Earth and a more distant star, the gravity of the foreground object bends and amplifies the light from the background star. The magnification follows a specific pattern that can be detected and measured with precision instruments. If the foreground object is sufficiently massive but completely dark, the signature is still visible even though the object causing it is not. That is how this black hole gave itself away, not by emitting anything, by bending light that was not its own. The estimated mass is between 7 and 10 solar masses, which places it firmly in the stellar mass category. The current velocity is approximately 31 kilometers per second, relative to the surrounding stars, which is faster than a leisurely drift but not extreme by cosmic standards. The most likely explanation for why it is moving at all rather than remaining stationary at the site of its formation connects to the physics of stellar death. When a massive star ends its life in a supernova explosion, the event is not always perfectly symmetrical. If the explosion is stronger on one side than the other, the remnant that forms in the collapse receives what physicists call a natal kick, a velocity imparted by the asymmetry of the explosion itself. The new black hole is essentially launched through space by the momentum of its own violent birth. The parent star is gone. The surrounding material has dispersed. What remains is a dark massive object with no anchor and nowhere to be. The significance of this detection extends beyond the specific object. It represents proof that the gravitational microlensing technique can successfully identify isolated stellar mass black holes and opens the possibility of systematic searches for a population that may be enormous. Current estimates suggest the Milky Way contains somewhere between 10 million and 100 million stellar mass black holes. We have directly identified approximately 50. The gap between those numbers means the vast majority of the black holes in our own galaxy are currently invisible to us. The detection of this wandering example suggests that population is now at least partially accessible to observation through methods that do not require the black hole to be actively consuming material. Move now from the question of where black holes are to the question of what they ultimately do. Stephen Hawking's 1974 theoretical work on black hole radiation introduced a concept that significantly complicated the previously simple picture of black holes as permanent features of the universe. Using a combination of general relativity and quantum mechanics, Hawking showed that black holes should not be completely stable. The quantum behavior of the vacuum near an event horizon should produce a faint thermal radiation that carries energy away from the black hole at an extremely slow rate, over timescales so vast they have no practical analog. In human experience, a black hole radiating in this way would gradually lose mass and eventually reach a state where the radiation and the remaining mass approach a crisis point. What happens at that crisis point is genuinely unknown. The mathematics of general relativity breaks down at the singularity inside a black hole. The mathematics of quantum mechanics, as currently formulated, does no incorporate gravity in a way that produces reliable predictions at those scales. The endpoint of Hawking evaporation sits precisely at the boundary where our two best physical theories cease to give coherent answers. Loop quantum gravity is one of the frameworks attempting to build a description of physics that works at those scales by treating space and time themselves as made of discrete quantized units rather than the continuous smooth fabric that general relativity assumes. Within this framework, some researchers have proposed that as a black hole shrinks through Hawking evaporation toward the scales where quantum effects dominate the collapse, does not continue to a singularity, but instead encounters a quantum pressure that reverses the infall. The black hole bounces, or what had been consuming everything begins expelling everything. A white hole. A white hole is the time reverse of a black hole. Where a black hole permits nothing to escape once it has crossed the event horizon, a white hole permits nothing to enter. Matter and energy emerge from it, but nothing from outside can penetrate it. The interior is permanently isolated from the exterior universe. Whatever falls into a black hole might in this framework eventually emerge from a white hole as the black hole completes its evaporation cycle. The practical inaccessibility of this process for any observer is essentially total. The timescale for a stellar mass black hole to evaporate through Hawking radiation is so incomprehensibly long that it dwarfs the current age of the universe by factors that have no meaningful comparison in everyday experience. Whatever happens at the end of that process exists in a future so remote that the stars currently forming will have been dark for longer than the present age of the universe by the time it occurs. But the theoretical significance is substantial. If black holes do not represent permanent endpoints of matter and energy, but rather extremely slow recycling mechanisms, the information paradox that has occupied theoretical physicists for decades takes on a different character. The question of whether information about the matter that falls into a black hole is preserved or destroyed connects directly to the question of what happens at the end of the evaporation process, and whether the white hole framework preserves what the black hole consumed. These questions currently have no empirical answers. The theoretical tools needed to address them properly do not fully exist yet. What the combination of Webb observations and the detection of isolated wandering black holes and the continuing theoretical work on quantum gravity is doing is establishing the observational and conceptual foundation that makes those answers eventually possible. What the James Webb Space Telescope has done to the study of black holes in the early universe is not simply add new data points to existing models. It has revealed that the models were describing a universe somewhat different from the one that actually existed. The little red dots, the disproportionately massive central black holes in underdeveloped early galaxies, the possibility that at least some supermassive black holes predated and influenced the galaxies around them rather than emerging from them. These discoveries are not refinements of the existing picture. They are challenges to it. The universe in its first billion years appears to have been producing structures and reaching scales of organization faster than the processes identified in the mature cosmos can account for. Something was happening in that early period that our models of galaxy formation and black hole growth have not yet fully captured. Whether the explanation involves direct collapse from massive gas clouds or dark matter dynamics or some mechanism not yet proposed, the observational evidence is now clear enough that the question cannot be set aside. We are at a specific moment in the history of astronomy where the instruments are finally capable of seeing the early universe in sufficient detail to test the models that were built from observations of the nearby and relatively recent cosmos. And what those instruments are finding is that the early universe was stranger and faster and more productive than the models expected. The black hole that should not exist according to the timelines. The wandering dark mass, detectable only by the light it bends on its way through our galaxy. The theoretical endpoint of evaporation that may reverse everything a black hole has spent billions of years consuming. These are not separate stories about exotic objects in distant corners of the cosmos. They are different angles on a single question that turns out to be more open than it appeared a decade ago. How does the universe actually build itself? And how confident should we be in the answer we had before Webb started looking?